In this video, we're going to look at two different topics. The first one is we're going to look at advanced energy profiles. So we've seen energy profiles before when there's only one step. Now we're going to look at how they look a little bit different for mechanisms. That's a pretty easy thing to understand. Then we're also going to take a deeper look at catalysts. In an earlier video, we talked about how catalysts make reactions go faster, even though they're not a reactant or a product. In this video, we're going to take a little bit more detailed look at how they do that and how that affects energy profiles. So first of all, let's take a look at an energy profile where we're taking into account that there could be more than one step in a mechanism for the reaction. This is an example of a reaction that's exothermic. We know that because the products have less energy stored in them than the reactants did. And it happens in two steps. And we know that because there are two humps, there are two peaks in this energy profile. We can also tell that the first step is going to be the rate determining step in the mechanism. And the reason for that is because its activation energy is way higher than the second step. So the first step will happen slow, and then the second step would happen faster. Here's another one. This is an endothermic reaction. We know that because the products have more energy stored in them than the reactants. We know that it happens in three steps because there are three peaks in this energy profile. And then if we look at the activation energies for the three steps in the mechanism, the second one has by far the largest activation energy, so that's going to be the rate determining step in this reaction. Now let's look at catalysts. There are two main ways that catalysts function in a chemical change. The first kind is homogeneous catalysts. The word part homo means same and gen means form. So these are catalysts that exist in the same form or the same phase as the reactants and the products. So they're almost like reactants and products, but they actually aren't. They participate in the reaction without themselves either being a reactant or the product. They're consumed in one step of a mechanism, and then later on they're produced in another step. And that's a way that we can spot them in a mechanism. If we have a product in a later step that was a reactant in an earlier step, that's a catalyst. And how they increase the reaction rate is by providing a pathway that has an overall activation energy that's lower. Here's an example. Hydrogen peroxide, H2O2, naturally decomposes into water and oxygen gas. So if you were to watch this reaction occur, you might be looking for bubbles of oxygen gas to see that the reaction is occurring. However, it's extremely slow if it's uncatalyzed. There are several ways that you can make this reaction go faster with catalysts, and one of them is by using the bromide ion. For example, if we added hydrogen bromide or hydrobromic acid to hydrogen peroxide, this is the hydrobromic acid. Remember, it's a strong acid, so it's going to split up. The bromine ion is the catalyst here. What it does is it reacts with hydrogen peroxide and produces water and bromine, Br2. This bromine is a brown-colored solution when it dissolves in water, that bromine molecule. This is a slow step. But then the bromine reacts with hydrogen peroxide and produces the bromide again, so we get it back. That's how we know it's a catalyst. It got consumed in the first step and we got it back in the second step. And then it produces oxygen gas, and that's much faster. Here's this reaction occurring. You can see that brown color increasing as more and more bromine is produced. And when it gets at its brownest, when they're the most Br2 present, then the reaction suddenly speeds way up, and that fast step consumes all that bromine, and you saw lots of bubbles of oxygen gas, and then it goes back to its original color because the bromide has all been restored and the brown-colored bromine got used up. When we look at energy profiles for reactions that occur with a catalyst, we can see that there's going to be a different version of a pathway from reactants to products that has a lower activation energy. So in this example, the uncatalyzed reaction is the red hump with a very large activation energy. The catalyzed reaction occurs in two steps. The first one is slow, the second one is fast, but both of them are much lower activation energy than the uncatalyzed reaction, and so the reaction goes faster. If we think about the Arrhenius equation, the reason for this is because the activation energy got lowered, and the activation energy being smaller makes the rate constant higher. This is generally what the shape of the curve would look like for the Arrhenius equation, where x is activation energy and y is rate constant. And we can see as the activation energy gets lower, the rate constant gets higher. And the rate constant being higher means that the rate is going to go faster if the concentrations don't change. So this would be an example of a homogeneous catalyst that has a fast first step. We know that the first step is faster because it has a lower activation energy than the second step. And we know the activation energy is lower because overall this curve, even the highest activation energy is lower than the uncatalyzed activation energy. The other kind of catalyst is called a heterogeneous catalyst. The word part hetero means different. So these are catalysts that exist in a different phase. A lot of times that phase is just a metal surface, like platinum or something like that, like in catalytic converters. And it's just a place for molecules and atoms and ions to stick to so that they don't bounce around as much in three-dimensional space, and it makes it easier for them to find each other so you can have more effective collisions. By removing that degree of freedom, by having them like slide around in a two-dimensional surface instead of bounce around in a three-dimensional surface, you remove a way for the particles to not hit each other, and that means they hit each other more often, which means more collisions that are effective, which means a higher reaction rate. Here's an example of something that benefits from a heterogeneous catalysis. This reaction is between hydrogen gas and carbon monoxide gas, and it can produce C7H16 and water vapor. In order for this reaction to occur, you have to have a 15/7 collision, all at the same time. 15 hydrogen particles have to collide with 7 carbon monoxide particles with the correct orientation for the reaction to occur. That's highly unlikely, and so this reaction rate would be impossibly slow without catalysis. But what we do is we provide a metal surface for these particles to stick to. So the hydrogen particles and the carbon monoxide particles can stick to the metal surface, and then they're only moving around on the surface, and it's much easier for them to find each other, and then you can build that C7H16 and water molecule products on that surface. Now, if we think back to the Arrhenius equation, lowering the activation energy is probably not the big deal here, although these catalysts might actually do that. Probably the bigger factor here is the frequency factor, because we are now providing an opportunity for more effective collisions. So that frequency factor is going to go up, and that's what's going to make the rate constant go up. You may have heard of enzymes before. These are biological catalysts, and they're heterogeneous catalysts. There's this thing called an enzyme. It's just a big, highly complicated molecule. And then a thing called a substrate, which is a smaller molecule, or sometimes it's a pair of molecules that are not going to find each other very easily at low temperatures because they're not moving around that fast. But this provides a place for them to sort of sit there and interact with each other. This is probably a more realistic picture because it shows things kind of at the atomic level. That big green thing is a very complicated molecule with probably thousands of atoms in it. And then there are these two particles that are going to interact with each other. The enzyme provides a little spot for them to sit because it's shaped just right. That puts them in close proximity to each other so that they can exchange that little particle fragment and produce a product. This is the reason that we can digest food, which is basically a burning process, even though our body temperatures are much lower than the temperature of a flame that's burning food, because we allow the particles to find each other better by providing that surface in the enzyme. We can digest food at normal body temperature instead of hundreds of degrees Fahrenheit.